In this next example, I have another triple integral that I want to convert into spherical coordinates. The integrand this time is x times y. The region we're integrating over I'm calling E, as I always do. And that region is cut out by the following inequalities. One of them is y is bigger than the absolute value of x. Then we have x squared plus y squared plus z squared is bigger than or equal to 1. And then finally x squared plus y squared plus quantity z minus 1 squared is less than or equal to 1. And to the surprise of absolutely no one, I'm going to start out by drawing some pictures. This solution is going to be a quadruple picture solution, so buckle up. Now, as always, I'll begin by attempting to draw the entire region in 3 dimensions, but this is going to be rough, so don't get too optimistic. But here's our 3-dimensional world. Let me start off with this first inequality. As always, a good way to treat inequalities is to think about their equality cases. So in green, I would get the equality y equals absolute value of x. What does this trace out? Well, in the xy plane, I know what the absolute value of x looks like. And then we have no restriction on z, so this is just a bent plane type thing, sitting above y equals the absolute value of x. The next inequality I'll treat in red. This would give me x squared plus y squared plus z squared equals 1. That's easy, that's a sphere of radius 1 centered at the origin. Now when I draw this sphere, I'm not going to try to draw the whole thing. I don't want to clutter the picture too much. So instead I'll draw some traces in relevant planes. The 2 green planes I care about for sure, so I'll draw the trace in those planes, and then I can draw the trace in the xy plane. We get a sliver of a ball that kind of looks like this. Finally, this third inequality I'll treat in blue. The equality case gives me another sphere, this time also of radius 1, but centered at the point 0, 0, 1. So it's shifted up a bit, exactly like in example 2. This is where the picture starts to look like it had a rough day, so don't look at this too closely, but again, I'm going to try to draw the trace of this sphere in the green planes, and then they kind of connect like this. And at this point, I don't even know what I'm looking at, but let's think about the inequalities that we were given. Y has to be bigger than the absolute value of x, which means on my picture here, we care about stuff to the right of this bent plane. Likewise, the middle inequality tells me that we care about stuff outside of the red sphere. And the last inequality tells me that we care about this stuff inside the blue sphere. So if you think really hard for a second, that'll give you this region here. And if you're looking at this and thinking, Joe, you just confused me more, I have no clue what's going on, let me show you a couple side view pictures. For example, what if we stood on the x-axis and looked at the region from that angle? In other words, we could look at the region in the YZ plane. In the YZ plane, we would see the red sphere, we would see the blue sphere, we would see the green planes that are kind of cutting out half of this region, and E is going to correspond to this shaded region here, outside of the red sphere, inside of the blue sphere. I think it's a lot easier to see what's going on from this view. And just for fun, another side view, what if we stood on the y-axis and looked at the xz plane? Well, again, we'll see the red sphere and the blue sphere and the region contained between them, and it would look something like this, roughly. Okay, so I'll give myself maybe a C+ for that first picture, but these other 2 pictures I think do a pretty good job of indicating what this region looks like. Now, as always, we need to describe the region in spherical coordinates, which means we need inequalities for rho, theta, and phi. And also, as always, I'm going to think about rho first. To get the bounds for rho, we want to think about walking along rays starting at the origin. And when I walk on these rays, I want to identify the lower bound and the upper bound based on my pictures. Based on these side views, it looks like the lower bound is cut out by the red sphere, because that's the first thing we cross when we enter the region. So what do? I take the algebraic equation for the red sphere, turn it into spherical coordinates. We get rho squared equals 1. Solve for our variable of interest, which is rho, and we get rho equals 1. So there's our lower bound for rho. And again, this should make sense just because the red sphere is exactly a centrally located sphere of radius 1. Likewise, when I think about the upper bound, when we walk along these rays, I keep walking until I hit the blue sphere. So that tells me that the upper bound is determined by the blue sphere equation. So I'll take that equation, and my goal is to turn it into spherical coordinates. I always think it's easier in this case to multiply out that squared quantity to get a z squared minus 2z plus 1. Then the 1's cancel out. I can move the 2z to the right-hand side. Then, this is easy to turn into spherical coordinates. I'll get rho squared equals 2 rho cosine phi is z. Again, solve for the variable of interest. We can do this by dividing by rho. We'll get rho equals 2 cosine phi. And there's our upper bound. This is exactly what happened in the previous example. Okay, moving on to theta. Now, because theta represents a rotational angle in the xy plane, I'm actually going to draw a fourth picture, which is the projection of this region onto the xy plane. When I do this, the region is mostly cut out by these green planes. I would see a picture like this. Now we want to think about sending theta counterclockwise starting from the positive x-axis. And by doing that, I can identify that both the lower bound and upper bound for theta are determined by the green planes. So, don't fix what isn't broken. We'll take that algebraic equation and turn it into spherical coordinates. This time we'll get rho sine phi sine theta equals absolute value of rho sine phi cosine theta. Something small to point out here is that, well, rho is always positive, and sine of phi is always positive. Phi always lives between 0 and pi, and hence sine of phi is never negative. That means that I don't have to worry about the absolute values on these two terms, and I can just divide both sides by rho sine phi. This leaves us with the equation sine of theta equals absolute value of cosine theta. And as usual, if you think about your unit circle for a second, you'll recognize that this happens when theta equals pi over 4 and 3 pi over 4. And that makes a lot of sense when we look at our picture in the xy plane. So there we go, we've got bounds for theta, and last we just have to deal with phi. So this is where the side view pictures really come in handy. Thinking about bounds for phi, I'm thinking about starting at the positive z-axis and swooping down to trace out the region. Now, because the region contains the z-axis, that means we're going to start phi at 0, so our lower bound will be 0. The trickier part is the upper bound. But as I swoop out, I recognize that the thing that's going to determine the upper bound is the point where the red and blue spheres intersect. That intersection point dictates how far I have to swoop out. Now, the red sphere and the blue sphere, we already figured out the equations for those involving spherical coordinates. So the upper bound for phi comes from the intersection of rho equals 1, rho equals 2 cosine phi. I'm interested in a bound for phi, so I'll set both of the rho expressions equal to each other. This gives me 1 equals 2 cosine phi. So cosine of phi is a half, and that means that phi is pi over 3. So there's our upper bound. So the hard part's over, we just have to convert the integral into spherical coordinates. The original integral we cared about was of x, y over this region. So what do we get? Our integrand we change using the spherical transformation equations. X is rho sine phi cosine theta, y is rho sine phi sine theta. The differentials I have to change with multiplication of the Jacobian. The Jacobian of the spherical coordinate transformation is rho squared sine phi. And then, like I mentioned in the previous video, usually it's a good idea to think about doing rho first, and then, for example, theta and phi. And this is another example where we have to do it this way because the row bounds that we cooked up depend on phi. So I'll put d rho on the inside, I'll do d theta d phi, pop in the bounds that we found earlier, and then we congratulate ourselves on a job well done. In this last example, we're given a region E. This time it's the upper half of the ball of radius 3 centered at the origin. And the prompt here is to compute the centroid of E. So now the first thing I'm going to do is actually not going to be draw a picture. It's going to be to remember what the hell a centroid is. So in words, what is a centroid? It's just the most average point in the region. In other words, it's the average of all of the x coordinates, all of the y coordinates, and all of the z coordinates, respectively. How do we compute such a thing? Well, the next thing to recall is how do we compute the average value of any function? If we're working in 3 dimensions, which we are in this case, the average value of a function f over some region E is given by the integral of that function divided by the volume of E. You've probably seen this kind of thing before, maybe with single variable integrals or double integrals, but this is just a generalization of how do you find the average of something? You add all of the somethings up and then divide by the total number of somethings you have. So for this problem, we want to compute the centroid of E. The next thing I'll write is just notation, but it will be the point x bar, y bar, and z bar, where what do these things mean? X bar just means the average x coordinate, y bar means the average y coordinate, etc. So how would we compute these things given what I wrote in the second thought bubble there? For x bar, the function that we care about on E is x. X is a function which eats any point in E and just returns the x value. So to compute the average x value of E, I'll integrate x over E and then divide by the volume. And it's exactly the same for y bar and z bar. To get the average y value, I'll integrate y over the region, divide by the volume, and to get z bar, I'll integrate z over the region and divide by the volume. And in case you just broke out into a cold sweat looking at this thinking, oh my god, we have to compute 4 different triple integrals, 3 of them for each coordinate and then a volume integral. Don't worry too much, it's not going to be as much work as you might think. First of all, I'll be a little lazy and I'll just claim that the volume of E is something that's relatively standard that we don't need to spend time talking about computing. In particular, remember that the volume of a ball of radius r is 4/3 pi r cubed. We can just probably assume that for this problem. But if you want to come up with a good, honest, self-contained solution, how could you compute such a thing? You can compute it with a triple integral, right? The volume of a ball would be given by a triple integral in spherical coordinates from 0 to r, 0 to 2 pi, and 0 to pi. And then in Euclidean coordinates, the function you would integrate is 1. So when you turn to spherical coordinates, you just pick up the Jacobian, rho squared sine phi. So if you get really bored, you can actually compute this, and you should get 4/3 pi r cubed, but we'll just assume that for now. Now, E isn't a whole ball, it's half of a ball, so the volume of that will be 1/2 times 4/3 pi r cubed, and r in this case is 3. So 4 over 2 is 2, and then 3 cubed over 3 is 3 squared, which is 9, so we get 2 times 9, which is 18 times pi. So one step of this calculation is done. The volume of E is 18 pi. Joe, do I have to specify the units, you may ask? No, we're in math class. So moving on, we need to compute x bar, y bar, and z bar. Next, I'll make another really clever observation that will save us a lot of work. In particular, for x and y, we can exploit symmetry of the region. This half ball that we care about is symmetric about the planes x equals 0 and y equals 0. So for example, x equals 0 is the yz plane. If you chopped E in half with the yz plane, it would cut it right down the middle, and the thing you get on either side looks exactly the same. Likewise, it exhibits symmetry across the xz plane, which is given by y equals 0. This is useful because, for example, the function x, this is an odd function with respect to x. And so with no work, I can say that this integral of x over e is going to be 0. And therefore, x bar is 0 divided by 18 pi, which is still 0. And if that makes you uneasy, then you can compute the integral if you want, sit down and convert it into spherical coordinates, and you should get 0. But this should also make sense geometrically. Look at the region. What are we computing here? We're computing the average x value. Well, the average x value is going to be in the middle of the x range, and that's at 0. So this makes a lot of sense. The same argument applies to y. Y is an odd function with respect to y. The region is symmetric about y equals 0, so by odd symmetry, with no work, I can say that the integral is 0. Therefore, y bar is 0. So the first two components of this point are both 0, and it remains to just compute z bar. Now this time we can't invoke odd symmetry. Z is an odd function with respect to z, but now the region's not symmetric over the plane z equals 0. We only live on one side of that plane, so odd symmetry doesn't tell us anything here. So unfortunately, we actually have to do some computation now, but it shouldn't be too hard. We'll start out with this integral that we care about. We're integrating over the interior of half of a sphere. So call me crazy, but I think spherical coordinates will be a good choice here. Setting up the bounds in this case is pretty straightforward. I'll blaze through this quickly, but I encourage you to make sure that this makes sense. Rho is going to go from 0 to 3. We'll swing theta all the way around from 0 to 2 pi. And then phi, because we're dealing with the top half of the sphere, we want to stop at the xy plane, which means phi is going to go from 0 to pi over 2. Then when I convert the integrand, z is rho cosine phi. Then I have to multiply by the Jacobian rho squared sine phi. And I've got d rho d theta d phi. From here, it's a straightforward integral calculation. I'll do it relatively quickly. For example, on the inside integral, with respect to rho, we have a rho to the third. So integrating that gives me rho to the fourth over 4. So when I plug in 3 and 0, I'm just left with a factor of 3 to the fourth over 4. And if your eyes haven't glazed over, you'll notice that I forgot to divide by 4. Don't panic, I'll catch it eventually. But for now, there should be a divided by 4 there. Next, I would integrate with respect to theta, and the story is the same. There are no thetas in the integrand. So I'll just pick up a factor of 2 pi minus 0. And that leaves us with an integral just in phi, from 0 to pi over 2 of cosine phi sine phi. This is easy to do with a u substitution. For example, call u sine of phi, then du is sitting right there in the integrand. Sine of 0 is 0, sine of pi over 2 is 1, so we end up with 0 to 1 of u, which, integrating that, gives me u squared over 2, plug in 1 and 0, and that leaves us with a half. And then up to the missing factor of 4, we're done. Z bar is going to be this number that we got divided by 18 pi. And we're about to learn a very important lesson in math, and also probably in science. I don't know much about science, but I'm guessing that this piece of advice applies in physics as well. I got to my final answer, and I got 9 over 4. And then, instead of stopping, putting the pen down, patting myself on the back, and getting a celebratory snack, what did I do? I asked myself, does this answer make sense? So I look at 9 halves, which I know is about 4.5. And then I look at my sphere, which I know has radius 3. I thought to myself, Joe, could the average z value of a point in the sphere be 4.5? No, that's absurd. An alarm sounds in my brain and I realize that I did something wrong. And it takes me a few seconds, but because I have a pretty nice organized solution, I can spot the error pretty quickly. That's what I get for trying to do two integrals in my head without writing anything. I would suggest not doing that on your next exam. So when you toss all those 4's in the denominator, we get 9/8 instead, which is like 1 point something. That makes a whole lot more sense. It really makes sense because halfway up the half sphere would be 1.5, but this half sphere is more weighted at the bottom, right? There's more stuff near the bottom, so it makes sense that the average z value will be less than 1.5. Anyway, that'll do it. There's the centroid. It's the 0.0098.